going to cover today spanning tree protocol. All right, so I'll just create a topology here, and that topology will be like this is going to be our switch 1, switch 2, and switch 3, and they're connected with each other through this link. And the interface names that they are having works like this. So you have FA0/1 and FA0/2. Then you have FA0/1, FA0/2, and you have FA0/1, FA0/2. Good. And you are also having some MAC address for this switch. So you have switch 1, you have switch 2, and you have switch 3. Switch 1 has a MAC address of 1111. Switch 2 has a MAC address of 2222, and switch 3 has a MAC address of 3333. Now, talking about spanning tree protocol itself. So talking about spanning tree protocol itself, whenever uh, whenever there is layer 2 loop, then spanning tree protocol does its job of protecting the network. Because what happens is whenever there is any, I would say, traffic coming in that switch doesn't really know about, what switch does is it forwards the traffic out on each and every interface that it knows about, right? And this is how it gets flooded out on this interface as well, and this interface as well, and this interface as well, and this interface as well. Makes sense to you? Now, whenever the traffic is like going on this interface and going on this interface as well, you can see there that the traffic kind of revolves in this scenario. And if this interface or this link also is up, then the traffic can come back to the switch while going through this. So in certain scenarios like this, you need to like put this, let's say this link down. Okay, so this link goes into blocking state, and we also call it as alternative mode. Makes sense to you? So even though this link is up, spanning tree protocol puts this link on hold. Okay, and only the primary link will be used. So if the traffic needs to go from here to here, then it will not go through this, it will go through the other way. Makes sense, because of the feasibility of the network and to keep the network loop free. So there is no configuration that you need to do in order to apply this spanning tree protocol. Okay, because by default every Cisco switch do participate in STP process. So every switch uses this particular spanning tree protocol in their working. But when the traffic goes from here, then the traffic can reach out over here as well and here as well. So the basically task is whenever there is a redundant network in your scenario, then STP does certain calculation, and based on those calculation, it elects a port that can go into blocking mode. And whenever that port is needed, that port can convert from blocking to forwarding mode as well. And then it can come back to a normal state and forward traffic. But that will only be done if it's required. Otherwise, the port will always remain blocked. Okay. And STP only gets implemented whenever it's, I would say, whenever there is redundancy in your network. There won't be any scenario for STP if the topology looks like this. If you have a switch over here, then if you have another switch over here, and then you have another switch connected over here, there is no STP scenario in this topology because there is no redundancy, there is just single path of connectivity. But if there is another switch and this is how you connect it, then I would say redundancy would be there. So that's why STP will play its role over here. Do you understand why do we actually need STP? In order to avoid layer 2 loops in your network when there is redundancy in place. Do you understand this? Perfect. Now, what happens is everything starts at a process, and we call this particular process as root bridge election. So, very first step of STP, okay, is called as a root bridge election. This root bridge election needs to be done. And what is root bridge? Root bridge is basically the master of the topology, which lets like other users know about how it's going. And by default, there are some configurations that are basically done on the device. So, spanning tree protocol does certain elections, and after executing those things, because if you know, spanning tree protocol automatically removes layer 2 switching loops by shutting down the redundant links. And as I have told you, that redundant link is kind of an additional link between two switches, and a redundant link is usually created for backup purposes. So when primary link is down, the redundant link can, I would say, help you in order to keep the network up and so. Okay, so I would say that STP is by default the protocol, and it actively monitors all the links of the network. Okay, because it exchanges some of the hello packets that we're going to talk about soon. So it basically finds out a redundant link, and it uses an algorithm that is called as spanning tree algorithm, STA, spanning tree algorithm. It uses this spanning tree algorithm in order to remove the unnecessary, I would say, and it creates a topology database, and then it finds out that which port needs to be blocked. But everything, as I told you, starts at a root bridge election. And what is root bridge election? It is basically to elect the master of the topology, which is also called as root bridge. So root bridge is the starting point of the STP topology. Whenever you have such topology, you need to of course have a root bridge. And to elect a root bridge from all the switches of the network, STP uses two parameters. So it contains root bridge election basically is done by exchanging something called BPDU. And what is BPDU is called as bridge protocol data unit. And this BPDU contains something called bridge ID, or I would just write it in a clear way, bridge ID. And the content of this bridge ID is priority value plus MAC address. Priority value is made up of 2 bytes plus MAC address is made up of 6 bytes. And in total, bridge ID is made up of 8 bytes. So this bridge ID is the content of the BPDU, and this BPDU is exchanged every 2 seconds within each and every switch that is present. And by default, the priority value is set to 32,768 by default on all the switches. Do you understand this? By default, the priority value is 32,768. Good. Then after that, whosoever has the lowest priority becomes the root bridge of that specific network. Do you get that? Now, as of now, in our topology, do we have any, I would say, a switch which has lower priority value? By default, all the switches have the same priority, right? So that's why the next tiebreaker will be MAC address, meaning whosoever has the lowest MAC address will become the root bridge. And who has lowest MAC address in our topology? Does switch 1 has it, switch 2 or switch 3? Correct. Switch 1 will be the lowest priority. That's why this particular device, switch 1, will become the root bridge. So we will name it as RB, root bridge. Perfect. Then this is what the first election is. Based on the bridge protocol data unit or BPDU, it gets elected. Okay. And switch 1's FA0 slash 1 and 0 slash 2 will always be on. They will never be blocked. Okay. So first task is basically to implement the or elect the elect the root bridge, and that's what we done with the help of BPDU. Then the next task, which will be task number 2, is to elect root port. So I would say root port election is done over here. Okay. And when we do root port election, I would say that root port election is done based on a value that is called as cost. So there are two type of values. One is interface cost, or to which we basically call as port cost, and the other one is link cost, which we also call it as path cost. Okay. Now you have multiple type of interfaces. One is Ethernet. Second one is fast Ethernet. Third one is gigabit Ethernet. Fourth one is 10 gigabit Ethernet. And to each and every link, there is predefined cost that is announced. So for Ethernet, the cost is 100. For fast Ethernet, the cost is 19. For gigabit Ethernet, the cost is 4. And for 10 gigabit Ethernet, the cost is 2. Okay. Now, if you have a link, like two switches are connecting together, and the link that they are using is FA0 slash 0 to FA0 slash 1. So, can I say that the cost to reach out from here to here is 19? Do you agree this? Perfect. And if I again add another switch over here and say FA0 slash 2 and FA0 slash 1, and can I say the cost to reach out from here to here is 38? All right. So that is exactly how you basically create the link. But let's take an example where the cost of the other link is not the same. So you don't have this fast Ethernet and you have this link that has at the one end, I would say the cost is FA0 slash 2, but at the other end you have a cost of gig 0 slash 0. So the root port, or I would say port cost for FA0 slash 2 is 19, and the port cost for gig 0 slash 0 is 4. Which one will be considered? The lowest one. Sorry, the highest one, which will be 19. Okay. So 19 will be considered as a path cost. But if this particular, I would say, link also is a gig Ethernet, that gig 0 slash 0, then the cost will be changed from 19 to 4, and the path cost becomes 4. So the entire path cost in order to reach out from source to destination will be 23. Do you all agree that? Okay. Now, after getting to know this cost and how this cost actually works, you need to understand what is root port. So root port basically is a port that every non-root bridge will have. And which are our non-root bridge switches? Non-root bridge in our topology is switch 2 and switch 3. And this switch 2 and switch 3 needs to elect one root port. You need to have a root port on each and every switch that is participating in this STP election. And which interface of switch 2 will be the root port? That is a question now. And also which interface of switch 3 will be the root port? So root port is elected to the port that has lowest distance or lowest cost in order to reach out to the root bridge. Meaning switch 2 has two interfaces that it can use in order to reach out to switch 1. Right? First interface is FA0 slash 2 and the second interface is this via FA0 slash 1. What would be the cost in order to reach out to the root bridge by using FA0 slash 2? Can I say 19? Right? Okay. Then what would be the alternate path that will be what's gonna be the cost of that? 19 plus 19, 38. Correct? Right? So can I say that the interface that uses FA0 slash 2 will make it reach out to the root bridge faster than the other interface? And that's why FA0 slash 2 of switch 2 will become a root port. Do you understand that? Great. Now, what is going to be the root port of switch 3? Is it going to be FA0 slash 1 or FA0 slash 2? FA0 slash 1, correct? So, because it has the lowest distance. So, you have root port as your FA0 slash 1. Then, we are left with electing the designated port. So, the third type of election that is done is electing designated port. And designated port election is done. And now by default, all the ports that are of root bridge are placed as designated port. So I will call these ports as designated port, meaning they will not be blocked ever. They will always be on. Correct? And how many interfaces are we left with now? We just have FA0 slash 1 and 0 slash 2, which is basically a link between switch 2 and switch 3. So one of them would be placed as a designated port. And who will be placed as designated port? The port which is connecting to the lowest MAC address that is there. You get that? And what's the lowest MAC address? Switch 2. That's why FA0 slash 1 of switch 2 will be placed as designated port. And then what is going to be the remaining port? The remaining port will be the choice will be made in order to electing the blocked port. So the remaining port, which is FA0 slash 2, will be placed as blocked port. Do you get that? This is exactly how you basically define the states for each and every interface that is present in your STP scenario. Now, why do we actually place this as DP and this as block? Because let's assume that this interface went down. So for switch 2 to reach out to switch 1, there is only one way that following this route. So when this interface goes down, the link needs to come up. And for that, at least one of the interface of that segment needs to be up so that this end can let the other end notify that, hey there, please turn yourself on. We gotta send some traffic ahead. That's why one of the port is placed into destinated port, so that whenever there is need, the device can forward the traffic via that interface. Do you understand this? Yeah, designated port basically is a port which stays there so that whenever there is any need for this link to come up, it can forward the information to the block 10 that, hey there, please turn yourself up. We gotta send some traffic ahead. If we keep this as block as well and this as block as well, the link will never come up. Make sense? All right. So that is exactly how you select and do all this process. Okay, so the first step is going to be election of root bridge. The second stage is going to be root port election. The third stage is going to be designated port election. The fourth port is going to be block port election. Okay, now as I told you that by default all the priorities are same. You can actually change this priority as well. But priority can only be changed in the multiples of 4096. Meaning you can either set it to 4096 or you can set to 8192 and then 16386 and then 20,000 something, sorry, then 12,000, 20,000, 24,000, 28,000, and 32,000 something something till 65,530 something. Do you understand this? So you cannot go ahead and change the port priority to, let's say, 100 or 200 or 300. It needs to be in multiple of 4096. All right. Then there are some STP, I would say, uh, port roles as well that gets assigned. Now these port roles or STP status, first state is disabled, which we refer to as DIS. The second stage is listening, which we advertise as LIS. The third stage is learning, which is LRN. The fourth stage is forwarding, which is FRD or FWD. And the fifth state is blocking, which is alternative, okay, or which is usually not alternative but BLK. Now by default the interface might be off, okay. Then as soon as the interface comes up, you would see that the interface will reach out to the listening mode. And then in listening mode, it only has the ability to participate into the BPDU election process, meaning root bridge election process. Okay, it cannot learn about the MAC addresses and it cannot forward the unicast or multicast frames. It can only forward BPDU traffic and participate into the root bridge election. That's all it can do in the listening mode. Then your switch after 15 seconds goes to learning mode. So I would say 15 seconds of time is required for going from listening to learning. And in learning mode, your switch can participate into BPDU election, or I would say root bridge election, and it can also build up MAC address table, meaning it can learn about MAC addresses in that specific, I would say, state. And then it stays there for another 15 seconds, and after 15 seconds, it goes into forwarding mode. And forwarding mode is the only mode where traffic can be forwarded by a switch port. So it does the job of forwarding the traffic. Okay. Also participating into BPDU by exchanging BPDU. And I would say the second thing was uh, to build up the MAC address table. So from disabled to go into forwarding, collectively it takes 30 seconds. Now, do you see that as soon as we turn off the link, the color of this particular link is red? Then it goes into amber. Sorry. Whenever it's in listening and learning, you will see an amber color. And then when it reaches out to forwarding, the color of the interface goes green. And if it's in blocking, you will also see a red color. Have you noticed that? Perfect. So that is exactly what happens. And when this particular link becomes like into forwarding mode, then you see the green light there. Till then, in the back end, STP process goes on. That's why it takes time for a switch port to turn on because there is a convergence time that STP takes. Okay, now there is also these timers, 15 seconds and 15 seconds as I mentioned. And we call these timers as STP timers. Okay, and the first time is BPDU hello, which is 2 seconds. So BPDU hellos are exchanged every 2 seconds by each and every switch. Then the next time is forward delay time. And forward delay time is of 15 seconds. This is the forward delay time. It takes the time from going into from listening to learning and learning to forwarding. We call this time as forward delay time. And the third time is max age time, which is 20 seconds. Meaning, if the switch doesn't get any BPDU for 20 seconds, it will announce that the link is down and it will turn on the blocked, I would say, port into a real port. Do you understand that? Just like hello time and dead time that we had in our routing processes, you also have a max age time over here as well. Max age time. Okay, and the max age time is of 20 seconds. Do you understand this now? STP timers? Perfect. That is exactly what will happen over here. And that's all we gotta talk about STP, okay, at the very basic level. Now what we will do, we will build up a topology and we will understand I would say a different topology over here and see how it works. Let's say you have got switch 1, then you have got switch 2, switch 3, and switch 4, and you connect it like this. And the interfaces are FA 0/1 0/2 0/1 0/1 0/2 1 0/2, like that. The MAC addresses are of course 1111 2222 33. Sorry. The priority is 32768. 16386, 32768, and 32768. This is what the details are of the switch. Correct? Do you understand the topology that we are having? Now tell me what is going to be the root bridge in this scenario. Switch 2 is going to be the root bridge. Why so? Because it has lowest priority. That's why I can say that switch 2 is going to be the root bridge. Correct? And both the ports will be placed as designated ports and designated ports. And Which switches are non-root bridges over here? Can I say switch 1, switch 3 and switch 4 are our non-root bridges. So we need to elect our root port on all these fours. So what is going to be the root port on switch 1? What is going to be the root port on switch 1? And people say FA0/1 is going to be the root port because it has lowest, I would say, path cost in order to reach out to the switch 2, which is our root bridge. That's why FA0/1 of switch 1 is going to be our root port. So this stands as root port. Then what is going to be the root port of our switch 4? It will be FA0/2. Perfect. So we will have FA0/2 as our root port because it has lowest path cost. Then what is going to happen at off switch 3? Because if we say that in order to reach out from here to here and from here to here, both the costs are same, right? So what's gonna happen? Is it gonna use FA0/1 of switch 3 or FA0/2 of switch 3? Now the decision gets done as the costs are same. It will consider the interface that is connected to the upward switch having lower MAC address. So switch 3 is connected to switch 1 and switch 3 is connected to switch 4 as well. Who has lower MAC address? Does switch 1 has lower MAC address or switch 4 has lower MAC address? It is switch 1, right? And that's why it will select the FA0/1 to be the root port of our switch 3. Do you all understand this? So you consider the upward connected switch, the uplink switch that you are connected with, and you basically select a port that is connected to a uplink switch which has lowest MAC address. Perfect. And then what will be the I would say now the link that is going upwards towards the FA0/2 of switch 1, this particular port will also be placed as designated port. This is not the root port, but every other port that is from designated port and blocked port will be named as, sorry, every port that is not a root port and blocked port will be named as designated port so that it can forward the traffic. So the FA0/2 of our switch 1 will act as a designated port. And which is the link that we are left with? The link that is left is this one. So one end of this particular link is going to be blocked and the other one is going to be selected as designated port. And which one will be blocked? Exactly. So switch 4's FA0/1 will be blocked. This is going to be blocked because it has higher MAC address. And then the other one will be placed as designated port. Make sense to you? So that is how you basically elect STP processes. Okay. So let's go ahead and see this particular STP, that how it actually works in action in our switch, okay, or in our packet tracer. So I will stop my screen sharing and share my other screen with you. So I will place the three switch topology over here and I'll just take these three switches and I will connect these switches together. right? This is what the topology looks like as of now. And you see, these lights are amber because the state in which they are currently, they might be in listening mode. And when I try to forward the traffic, then they come into forwarding mode. But you can see that this link is no longer up. This is still down. Do you see that? The red dot over there? So STP has done its work of choosing which port needs to be elected as root ports and which port needs to be elected as designated or so. Correct? And you can verify this by looking at or by using a command call. Let's go to our switch 1. This is our switch 1, right? So I'll name it as switch 1. This one is acting as switch 2 and this one is acting as switch 3. Okay, so I will go on my switch 1 and go to the CLI and use enable and then conf t and then say you can just name this as hostname sw1, and then I would say you can just check it with show uh, spanning tree. Sorry, you can use a command called from the enable mode show spanning tree. That's it. Show spanning tree can be used, and then you can see this over here that this is the information that you see. Okay, that's all the STP information that you have. So it is showing you that currently you just have VLAN number 1 that is configured, and this the protocol that is that STP is using is powered by IEEE, and then this is the information about your root bridge. Okay, the root ID means information about your root bridge, and bridge ID means the information about your local switch. Okay, so you see the root ID says that the priority of the root bridge is this, the MAC address of the root bridge is this, and it says that this bridge itself is the root. So the switch, our SW1 is acting as the root bridge because you can see the MAC address of the root bridge and the MAC address of the local switch is kind of same there. That's why you can see that this is the root bridge. And then you have the timers, and this is the important information that you see. So you have FA0/1 and FA0/2 are in place. And as I told you that all the ports of the root bridge will always be in designated mode. They will never be blocked. So the status of that specific, I would say, interface is forwarding and forwarding mode. The cost is 19 and 19. You can ignore the priority and type for now. Okay, that's none of your concern as of now. So this is what the detail is. Then if we go on switch 2, see FA0/1 is the shortest way possible for the switch 2 to reach out to the root bridge. So when we check the information on our switch 2, enable conf t do show spanning, let's say, you can see that FA0/1 is the root port and the other one is designated port. Do you see that? And this is the information of the root bridge, that the priority is this, the MAC address of the root bridge is this, the cost that is used in order to reach out to the root bridge is 90, the port that is making you reach out to the root bridge is FA0/1, and the timers, and this is the local information. Yes, STP is automatically enabled by default in each and every switch that you have. Okay, and that's the port ranges that you have. Then if we go on our switch 3 and check the same information, you will see there that enable and show spanning. And you can see that this is the information of the root bridge. Okay, and that's the information about local switch, but the FA0/1 here is blocked. This is the FA0/1, it is in alternative mode and the state is blocked. And FA0/2 is the root port. that is in forwarding mode, which is reaching out to the root bridge in the shortest way possible. Do you understand this? Perfect. Then there is also one more thing that is called as, this was about STP, but then there is other thing that is called as Portfast. So what is Portfast? Portfast is a term that is used for end devices that gets connected with the STP, because this is kind of a security feature of STP. There are others as well. We are not going to talk about all of them, but yeah, Portfast is one of them that is used. And what Portfast does is, let's assume that there is a user that is connected with this particular link. And as I told you, every 2 seconds, these switches do talk about with each other with the help of BPDUs. You see the interfaces again, I will show you. Show spanning. You see, the interface is FA0/3 and currently it is in listening mode. You get that? And then I would again check it. Now it is in learning mode. And then after some time, it will go green, and then it will, you see the green, and now it is in forwarding mode. Do you understand this? So that's the time that is taken by STP for the information to come up. Now, when I talked with you that it is also possible that you want to make some other switch as your root bridge. It should not be mandatory that before, like I would say, there is possibility that your switch 2 is kind of a layer 3 switch, and layer 3 switch is better in processing the frames than layer 2 switch, faster and efficient. So, but the priority in the MAC address is not lower than SW1. So by default, SW1 becomes the root port of your topology, sorry, root bridge of your topology. But you want to make SW2 as your root bridge. So what you will need to do, you will need to basically change the priority of this particular switch. And you can say that you can change the priority by using a command that's spanning tree and then VLAN 1, and then you can say priority, and then you can mention priority between 0 to 61440, but in the multiples of 4096. So I can set a priority of 8192, let's say. And when I said that, you can see that the interfaces again went down, some of the interfaces. And when I reschedule that, this interface came up and this became down now. Do you see that? So when I go to switch 2 and check do show spanning, then you can actually check that my switch 2 has become the root bridge over here, and the priority of this particular is 8193. Now how this 8193 is made up of, 8192 is by default the priority plus the VLAN number. Okay, that is how it becomes 8193. And then you can see that switch 3's FA0/2 has become blocked now. Do you understand? This is how the information changes. So you can always play around with with making the root bridge manually, but be sure that what you are doing to your production. Then after that, when we were talking about Portfast, so Portfast is a security feature that is applied on the end devices. So when you saw that as I connected this particular link with the end device, the FA0/3 was also transitioning from listening to learning and learning to forwarding. Now, in that case, let's say that this user is not a genuine user and it is an attacker, and he is using kind of a Kali Linux machine, and then he kind of builds up a packet that is nothing but a BPDU, and he sends up a BPDU message on this FA0/3 frame. And what the information he sends in that BPDU frame is a priority that is set to 4096. Do you understand that? Right? So if this particular BPDU or if this particular attacker sends a BPDU on switch 3 with the lowest priority, what is going to happen? The switch 3 will start assuming the PC that is connected on FA0/3 as the root bridge, and it will give all the VLAN information and other information to that attacker. That's why, to avoid such exposure of network to the unnecessary users, we configure Portfast onto the ports that are being connected or to with the end device, so that STP is not calculated or STP doesn't work on these ports or these links. So how do you do that? You go to interface, which is FA0/3, and then you configure it as spanning tree uh, Portfast. Okay, this is the command that you use, and you say spanning tree Portfast and hit enter. Okay, it says Portfast should only be enabled on ports connected to a single host. Connecting hubs, concentrators, or switches bridges is not, I would say, recommended or so. So that is what it says. And it says Portfast has been configured, but will only have effect when the interface is a non-trunking mode. And now your port will not participate, and say do show spanning, and you see that your FA0/3 will again be as designated ports, and it will not receive BPDU frames again. Okay, go ahead, see this particular lab and try to figure out by connecting 4 devices or 3 devices and see what the status changes. Okay, the command to configure port fast was spanning tree port fast. That is all. Go to the interface and use spanning tree port fast. Okay, just try this lab and we'll continue the next topic. I hope you're done with the lab, and then we will move to the next one, which is about ether channels. So I'll just delete this thing, and then what we are going to talk about is ether channels. Now what ether channel means is whenever you have multiple links that are placed in your topology. So let's say you have redundancy like this, from switch 1 to switch 2 you have 4 links, let's say, that are connected together. Now you see, after doing the STP calculation, you can figure that out that all the links at one side are green, but at the other side, the only one link is working. And why so? Because if you just check out on to switch 2, I will go to say show spanning tree. Then you can see that this is basically a root bridge. That's why all the links are turned, or all the links have been configured as the designated links and are in forwarding mode, because this is the root bridge. The ports cannot go blocking. The ports cannot go in blocking mode over here. But on the other end, you can see that when I check my spanning tree, show spanning, you can see that these alternate, alternate, and alternate, meaning that only one link is working and the other link is down. The other 3 links are down. What will happen to the other 3 links if the primary goes down? So let's go to conft and say interface FA0/2 and say, sorry, interface FA0/1 and say shutdown. So primary link went down, and then if you see after some time, you can see that do show spanning. Now you see FA0/2 became the root, and then it has been placed into forwarding mode. And if this also goes down, then the third one will become the green, and the fourth one will become green accordingly. Do you understand how this works? Because STP can only keep one link up at a time. Now, in order to, I would say, remove such kind of error, what do? We create ether channels, meaning that we basically bundle all these links into one group, and that one group starts acting as this is a single link. Okay, and that link can be used in order to forward traffic and like do the load balancing over there by using ether channel concept. And how do you actually do that? you basically go on each and every switch. The config is pretty simple, and you select the range of interfaces that you have. Okay, and now you can see all the links have this type as point to point. So all the links are point to point links. After that, you basically select a range of interface, says interface range FA0/1 hyphen 4, right? And then you put them into one group by using a command channel group. Okay, and then you number that specific group something like 1, and the numbering can be done between 1 to 6, so you can have maximum 6 groups like this. Okay, so you go and say channel group 1 and say mode on. Okay, that is what you say, mode on, and then you apply this particular command, and then you go on the other end as well and say conf t interface range fa0/1 hyphen 4 channel group 1 mode on. And once you do that, you can see that the links will go down and it will again come up. And after doing fast forwarding it, you can see over there that now all the links are green. You see that? And then if you check that out, do show spanning, then you can see that there is just one link which is called as port channel 1. Okay, PO1. And now it is the root port, and in the forwarding state, and the cost has been divided. Now the cost of that entire link is just 7. Okay, and the priority is this value, and the type is shared. Now it is not a point to point link anymore, it is a shared link. That is how it's working. Make sense to you? And you can also see that if I just perform do show IP interface brief, then you will see port channel 1 as another interface that is that has came up. So that is basically given to the ether channel, and you can also select or verify your ether channel by running a command do show ether channel. And you can see that the group number is 1. The group state is layer 2. It's a layer 2 ether channel. You can also build a layer 3 ether channel as well in multi-layer switch. The ports that have been placed in the group are 4. Maximum ports that are selected are 8. And the port channel number is the total port channels that you have is 1. And maximum port channel that you have also is 1. Okay, so you can figure that out based on this information as well, that how it is listed. And if one of this link goes down, then the other three will still keep on functioning. Make sense? So that's exactly how ether channel works. You get that? You cannot assign IP address as of now, as they are layer 2 interfaces. Okay, the cost just does the division according to the bandwidth that they're sharing. So when the 100 Mbps link has a bandwidth of 19, and 1000, I would say 1000 Mbps link would have a cost of 4. So when that particular cost gets divided and makes up to 400 Mbps, then the cost becomes 7. It's just internal configuration, or I would say algorithm, that it works accordingly. There is nothing manually that has been done. Okay, so the commands that are there is interface range fa0/1 to 4, and then you say channel group 1 mode on. Okay, and to verify that, you can just use show ether channel or show spanning tree and show ether channels. These are the commands that you can use. So go ahead, try to configure this ether channel and let me know when you're done. Yeah, that will basically change the bandwidth of the link, and it will be a shared bandwidth of 400 MB now. It's not like the speed of that particular data will become 400, but whenever, if there are 4 links that are working to send some traffic between switch 1 to switch 2, so you will effectively see the differences. Okay, that's how it works. So your one data cannot go with the speed of 400. Your multiple data will be shared across multiple links. That's how the speed kind of increases of sharing data between them. So that was all that we had to cover today. I hope you understood the concept of STP and Ether channels, and we're good for the session today. Tomorrow we'll explore things about IP services and we'll see how things goes. Are we good? So I hope you understood the STP and Ether channels, and thank you so much for tuning in. We'll guys continue in tomorrow's session. So thanks for tuning in. Take care of yourself. Bye bye.